Good morning. The next problem is to design a digital butterworth filter satisfying the constraint 0.707, which is less than or equivalent to modulus of h of e power j omega less than or equivalent to 1 for 0 less than or equivalent to omega less than or equivalent to pi by 2, and for the value h of e power j omega less than or equivalent to zero point 0.2 for 3 pi by 4 less than or equivalent to omega less than or equivalent to pi, with t is equivalent to 1 second using bilinear transformation. Okay. So from the given problem, first of all, we are in need to know what are all the given data. So what about the passband attenuation alpha p is equivalent to 0.707. Okay. So whereas the passband frequency, which is given to be the maximum value 5 by 2. For stop band attenuation, it is given as alpha s is equivalent to 0.2, and the stop band frequency is given as 3 pi by 4. Okay. So the first thing we have to find out the in attenuation in decibels. So we'll be know that the attenuation formula is equivalent to 20 logarithmic of the passband value. Okay. So alpha p is equivalent to minus 20 logarithmic of 0.707, which is equivalent to 3.0116 decibels. Whereas stop band attenuation, 20 logarithmic of the value. So 20 logarithmic of 0.2, which is equivalent to 13.9794 decibels. Okay. And then the next we have to find out we have determined the value of t and pre-warping the frequency. Okay. So if t is not, okay, with the t is equivalent to 1 second is given over that. And we know the relationship for finding of your pre-warping frequency. Omega p is equivalent to 2 by t tan omega p t divided by 2. Similarly, for omega s is equivalent to 2 by t tan omega s t divided by 2. So we'll be replacing t is equivalent to 1, and we'll be having of an omega p is equivalent to pi by 2. So pi by 2 by 2 will be pi by 4. Tan pi by 4, we know that 1. Upper we'll be getting of an 2 radian per second. Similarly, in the case of that, find the value of tan 3 pi by 8, which has multiplied by 2. So which is equivalent to 4.828 radian per second. Okay. So that is the second step. Third step, we are in need to find the order of the filter. N should be greater than or equivalent to log to the base 10 square root of 10 to the power of 0.1 alpha p minus 1 divided by 10 to the power of 0.1 alpha s minus 1 divided by log to the base 10 of omega s divided by omega p. Okay. So we'll be n should be greater than or equivalent to log of 10 to the power of 0.1. Substitute over value of alpha p and alpha s, and then we can able to find the value of n should be greater than or equivalent to 1.8017, and we have to rounding off the next higher value n is equivalent to 2. So what is the normalized transfer function? We know that HA of S is equivalent to 1 by S squared plus root 2 S plus 1. Okay. And then we have to find out the cutoff frequency. So which is nothing but an omega S, it is omega divided by 10 to the power of 0.1 alpha p minus 1 divided by 1 by 2n. So by substituting all that, we can able to find the cutoff frequency is equivalent to 2 radian per second. That is your fifth step. Sixth step, we have to find the transfer function h of s. So we'll be replacing s. So we'll be replacing s is equivalent to s by 2, because we'll be finding the transfer function over on it. So since it is a low pass filter, so we'll be replacing by s by 2. Whereas in the case of my high pass, omega c by 2. Okay. So we'll be having of omega c by s. Okay. So we'll be having of an s by 2 the whole square plus root 2 into s by 2 plus 1. By simplifying the expression, so s squared by 4 will be getting, so simplifying all this value, we'll be getting of an s squared plus 2.828 s plus 4, numerator factor will be 4 over on. Okay. Then after that, we have to apply bilinear transformation. What we'll be doing in the case of an bilinear, we have to replace s is equivalent to 2 by t of 1 minus z power minus 1 divided by 1 plus z power minus 1. So replace over on it, simplify the value. So what will be getting 2 by t is equivalent to 1 minus z power minus 1 plus 2.828, that is into 2 will be 5.656 into 1 minus z power minus 2 Okay, and then we'll be having of an plus 4 into 1 plus z power minus 1. So then after that, this will be goes into an numerator. So simplifying this expression, so what will be getting 4 minus 4 z power minus 1. So here we'll be having of an 4 plus 4 z power minus 1. So that will be getting cancelled. So we'll be getting of an so 8 in 8, take 8 be out. So 1 plus 5.656 divided by 8 will be 0.1716 z power minus 1. So 4 divided by 8 will be 1 by 2. So we'll be taking over that. So it will be equivalent to 0.2929 into 1 plus z power minus 1 divided by 1 plus 0.1716 z power minus 2. So for all, what you are doing over that. So first thing, we have selected the passband and stopband attenuation in decibel. Second, we are determined the pre-warping frequency. Third one, we determine the order of the filter. Fourth step, we have to rounding off the filter. Fifth step, we have done the normalized transfer function. Sixth, we have find out the cutoff frequency. Seventh step, we'll be replacing the transfer function. If it is a low pass, it is nothing but an S by omega C. If it is to be a high pass, we have to replace by omega C by S. And seventh step, we'll be applying the bilinear transformation to obtain the digital filter, and then final expression will be getting over on it. The same problem we are going to consider now. By that, we are going to find out the impulse invariant method. By using of an impulse invariant method, we are going to design a digital butterworth filter. Okay, so what we'll be doing over there? We are going to have a given data alpha p is equivalent to 0.707, passband frequency is equivalent to pi by 2, stopband attenuation is equivalent to 0.2, stopband frequency is 3 pi by 4. Now we will be specifying the passband and stopband attenuation in decibel. So use the formula of 20 logarithmic of an alpha p and alpha s, and found out to be 3.0116 decibel and 13.9794 decibel over on it. Okay, so we'll be determining the analog frequencies. That is having a pre-warping omega p and omega s. Okay, so the relation is nothing but an omega p into t, omega s into t. So we'll have of an pi by 2, because in the case of an impulse invariance, we'll be using of 4 order. Okay, so t is equivalent to 1, pi by 2, this value will be pi by 4. So what is the formula for finding of an order of filter? N should be greater than or equivalent to log to the base 10, 10 to the square root of 10 to the power of 0.1 alpha s minus 1 divided by so we'll be having of an log 10 to the pi of omega s divided by omega p. Okay, so when we are doing up an order of the filter, so n should be greater than or equivalent to log to the base 10. So we will be getting of an substituting all these values 0.998 divided by 23.945, and the final answer we are getting that n should be greater than or equivalent to 3.924. Okay, so that will be rounding off into an next higher value. So n is equivalent to 4 over that. Okay, so what we'll be getting? The value of n is equivalent to 4. The next we have to find the normalized transfer function. We know that the HA of S is equivalent to 1 by S squared plus 0.76537 is plus 1 into S squared plus 1 plus 8.74 S plus 1. Okay, the next thing we will be getting of an cutoff frequency. So cutoff frequency is equivalent to omega p divided by 10 to the power of 0.21 p minus 1 into of 1 by 2n. Okay, so it is equivalent to pi by 2 of 10 to the power of 0.1 into, so substitute the value over on it, divided minus 1 by 1 by 2 into 4. So we can able to find the value of cutoff frequency is equivalent to 1.57 radian per second. Since we are designing a low pass filter, we will be finding off by S by 1 by 0.7. We have to replace over on it. So replace over that, what will be getting of an S by 1.57 the whole square plus 0.76537 S plus 1 into of an S squared plus 1.8477 S plus 1. Okay, so then you take a cross multiplication, simplify the expression. So we will be getting of an 1.57 to the whole to the power of 4 divided by S squared plus 1.202 S plus 2.465 S squared Similarly, plus 2.902s plus 2.465. Okay, so we have to take the partial fraction expansion. So we'll by partial fraction, we'll be having often two different factors. One to be the a divided by 1 plus 1.45 plus j zero point 0.6 plus a star divided by s plus 1.45 minus j zero point 0.6 plus b divided by s plus 0.6 plus 1.45 j plus b star by s plus 0.6 minus 1.45 j. Okay, so we will be computing a and a star by replacing s is equivalent to 1.4 minus 1.45 minus j zero point 0.6. So then we'll be doing the cross multiplication and substituting over on it. Then after that, we'll be finding the value of a is equivalent to 0.7253 plus j 1.754. Actually, the complex conjugate value of a will be the next time. But what will be getting over on it? We'll be getting off an a star is equivalent to 0.7253 minus j 1.754. Similarly, we have to find the value of b and b star. So in order to find that, we have to replace s is equivalent to minus 0.6 minus j 1.45 minus 0.6 minus j 1.45. So replace over on it. So what will be getting over it? Then substitute over that, we'll be getting of a b value equivalent to minus 0.7253 minus j 0.3, and the b star value will be equivalent to minus 0.7253 plus j 0.3. Again, this is also will be the complex conjugate value of b. So by substituting the value of a star, b and b star in the expression of an h of s, then it will become 0.7253 plus j 1.754 divided by s minus of minus 1.45 minus j 0.6 plus 0.7253 minus j 1.754 divided by s minus of minus 1.45 plus j 0.6 plus minus 0.7253 minus 0.3j divided by s minus of minus 0.6 minus j 1.45 plus minus 0.7253 plus 0.3j divided by s minus of minus 0.6 plus j 1.45. Okay, and then we know that the value of t is equivalent to, once again, so in order to replace h of s into h of z, we have to use the transformation summation k is equivalent to 1 to n ck divided by 1 minus e power, that is x minus pi has to be replaced by 1 minus e power pit z power minus 1. So replace the Cole's value over here, e power minus 1.45, e power minus j 0.6. Okay. Similarly, the next value, e power minus 0.6, e power minus j 1.45. So simplifying all this expression, so finally h of z is equivalent to 1.454 plus 0.1839 z inverse divided by 1 minus 0.387 z inverse plus 0.055 z power minus 2 minus 1.54 plus 0.2307 z power minus 10 divided by 1 minus 0.1322 z power minus 10 plus 0.301 z power minus 2. So this is the way to design the IAR filter using bilinear transformation and impulse invariance filter. Okay, so we'll see you on tomorrow. Thank you all.